Exercise 2163 is talking about benzyl acetate. If you've ever smelled jasmine flowers or gardenias, that delicious odor is partly coming from benzyl acetate, and so they're introducing it here as a pleasant-smelling ester found in the essential oil of jasmine flowers and used in many perfume formulations. Starting with benzene and using any other reagents of your choice, design an efficient synthesis for benzyl acetate. Here it is. You can see it's an ester. You've got a carbon double bonded to oxygen, single bonded to an ether, so that's an ester. And it's remarkable that you can take benzene, the vapors of gasoline, and turn it into something that smells so wonderful and that's used in a perfume. And it's not so complicated of a molecule. So how can we do this? There are actually a couple ways. Now, when you first look at this, hopefully after this chapter, you would see the ester and you'd say, I could take this can come in as a nucleophile and could replace, for example, an acid chloride, the chlorine on an acid chloride. And so you could do a nucleophilic acyl substitution with that. But that's sort of the last step. We have to get this first. But now that we see that connection between the nucleophilic acyl substitution, the nucleophile that has to come in, and the leaving group that would leave, we can think about how we can turn benzene into the nucleophile there in red, which is really this. Now, there doesn't have the hydrogen there. The hydrogen is there to stabilize it before it attacks. There are a couple ways you can make this happen. The first way, you could see that you have a carbon-to-carbon bond that you need to form. Adding a carbon onto a benzene ring, well, that is most often Friedel-Crafts. So you can do a Friedel-Crafts alkylation. You can use CH3Cl, there's our one carbon that we're adding, and then AlCl3. Remember, when you do a Friedel-Crafts alkylation, you always have to worry about whether you'll have a carbocation rearrangement, because those can happen in the Friedel-Crafts alkylations. If you want to avoid those, then do a Friedel-Crafts acylation. But here, we only have one carbon, so there's nowhere that the carbocation could go. So you could do a Friedel-Crafts alkylation here. That would put the methyl group on the benzene ring. And once you have that, you can sort of think of this in a couple ways. You could think of it as an oxidation, in which case you can use a strong oxidizing. So let's say you can use a strong oxidizing agent like sodium dichromate and water and sulfuric acid, and that would bring it to a carboxylic acid, so benzoic acid. And then you could reduce it, treat it with a strong reducing agent like lithium aluminum hydride, followed by water to do the proton transfers to stabilize the charges, and that would give you your alcohol. So that's one way. Or you can think about this as a sort of substitution reaction. You could put a good leaving group on there using N-bromosuccinimide and light. That adds a bromine onto the benzylic position, and then you can treat that with an OH nucleophile. And you do an SN2 reaction and get that same product. Or you can take a different approach altogether from this whole thing. You can take benzene and say, you know what? I don't want to do Friedel-Crafts. I love Grignard reagents. I've loved them since the first moment I saw them. All I want to do all day are Grignard reagents, Grignard reactions. So how can I do a Grignard reagent here? Well, first you can add a bromine onto the benzene ring, so Br2 and FeBr3. That FeBr3 turns the bromine into an amazing electrophile with a full positive charge that even benzene can't resist. You get the bromine on there. Once you have the bromine, you're almost at your Grignard reagent. Just dunk some solid magnesium in. It'll insert itself in between the carbon and the bromine, and you'll have this Grignard reagent here. that carbon nucleophile. You could react that. We just want one carbon with an oxygen on it. To make it a good electrophile, we could make it a double bond, so we could react it with formaldehyde. And this carbon here is really a nucleophile. The magnesium is there to stabilize it, but that carbon could attack the slightly positive carbon here, kick that open. So you'd have this, and then just use some water to do a proton transfer to stabilize that. So you have, like, the world is your oyster. Look at how many paths you can take using all the knowledge you've gained this semester to make this happen. If for some reason any of these paths get stuck, you use another one. Your creativity is the limit. So once we have this alcohol, we can just react it as the nucleophile, or I should put that in a different color. Once we have that alcohol, we can use it as the nucleophile to replace the chlorine in this ethanoyl chloride. So we have that, whichever one of those you use. If you treated it with this ethanoyl chloride, and here actually let me put that on the other side. You'll replace the Cl, and you'd probably want to put some pyridine in here, so that, remember, pyridine is this sort of benzene with one of the carbons replaced by a nitrogen. The lone pairs can act as a base, and they'd steal the H off. What you'd get is your nucleophile replacing the chlorine leaving group. So you'd have the oxygen, and then double bond to oxygen and the carbon. So notice how your nucleophile replaced the chlorine. And you'll notice that the hydrogen is missing. Where'd the hydrogen go? It went to the pyridine. So pyridine would accept that H+ and become pyridinium. The P in PCC, pyridinium. So that H that we see here, that's not in our product, that is transferred by a proton transfer to pyridine to become pyridinium. And there it is, our benzyl acetate. The smell of gardenias, the smell of jasmine flowers, an ingredient in perfumes, and all created by these magical recipes.